Okay, YouTube, in this video we're going to be discussing powers of complex numbers. That is, if we have just some complex number, say a plus bi, it could be written in standard form, and I wanted to take this to the nth power, what we end up doing is foiling, and you just foil and you foil and you foil and you distribute, and anything like, 3 or more here, even with binomial expansions, it's an annoyance because then you have to reduce your powers of I. So there's a much cleaner way to actually conceive of powers of a complex number, and that is if we write it in r CIS theta form, or r cosine theta plus I sine theta. If we were to write it in this form and then raise it to the nth power, it actually becomes much cleaner, and I want to explore kind of why this happens. We, in the last video and the video before that, looked at products of complex numbers in trig form, and we said that when you multiply a number times itself, well, let alone I guess a number times itself, but a complex number times a complex number in trig form, you really just multiply the modulus values in the front, or the r distance, and then you would add the arguments of the direction angles here. So when I say z squared, I'm going to write it like this. I'm going to say r CIS theta times r CIS theta. I'm going to use the abbreviated form, and what we really get is this. We get r times r, and then we get CIS theta plus theta. So we end up with this, really, we get r squared, and then we get CIS, let me clean that up here, 2 theta. Now, this is r squared, and I bring this up because when we look at r cubed now, I'm going to say that really I'm just going to take r squared, which is this, r squared CIS 2 theta. And I'm going to take that times another r CIS theta, building in the third factor of r CIS theta. And if we multiply these r's in front, then I get r squared times r. Going a little faster this time, I say that's r cubed, and I would get CIS 2 theta plus 1 theta is 3 theta. And I think that building on this now, this is our complex number to the third power if it's written in trig form. We say take that number, and if we multiply it again by another r CIS theta, what we end up with is yielding this kind of pattern here where we're seeing that really what's happening is when we take a complex number in trigonometric form to a power, what we're really doing is each time adding on another factor of r in the front and another, angle theta in here in our argument. So in general, I'd say, looking at something like this, r CIS theta to the n, we can summarize this and say, look, if I'm taking r cosine I sine theta to the nth power, I'm always going to have to take r times itself n times. So I'm always going to get r to the nth in front. And as far as what the CIS is going to be, since I'm adding theta to itself n times, I'm going to have to say that I have n of these total thetas. And this actually is a very important theorem when it comes to powers of complex numbers. It's called DeMoivre's theorem. And DeMoivre's theorem states that if you have a complex number in trig form, see, that's the thing. I mean, if it's in standard, can do it. Convert it to trig, we can do this, okay? But we say if z is this number r CIS theta, or cosine theta plus I sine theta, so we have our standard form of our complex number here, but with a direction, kind of being the main component there, and then a distance here. So we say this is a complex number and n is a positive integer. Then when you raise this complex to this positive integer n right here, then what it yields is the fact that we're always going to take r times itself that many times. So we just get r to the n, and then we get cosine n theta plus I sine n theta, where we take this n and make it the power of the r and we multiply it by the angle. That's it. That's all you got to do, okay? So we say if leaving in trig form, reduce the angle so that it's less than 1 positive rotation. And that is to say, we're always going to put our angle, if we're leaving it in trig form, is an angle between 0 and 360. Anything over that, we're going to need to reduce it. That's all that means. So let's go ahead and take a look at an example here where this would really come in handy. We could do this with Pascal's triangle, binomial expansions, but like I said, it's going to be messy with reduction of i's and combining like terms. So what I'm going to choose to do here is I'm going to choose to take this complex number that is currently listed in standard form, and I'm going to identify a and b because what I want to do is convert this into trig form. So let's go ahead and start by sketching a picture of this. A lot of people get intimidated by this. We say, okay, -1, but up square root of 3. Well, this is left 1, I would say. Up 1 would be here, 2 would be here. Square root of 4 would be, less than 2, and square root of 1 would, be bigger than 1. So this is somewhere in between here, this square root of 3. So I'm going to say it's about right here. That's all I know. So here's our complex number graph. We need r, and we need theta. And what we were told were neither of these, but we were told that the left side of this triangle, the bottom side, is -1, and we know that this is square root of 3. That being said, Let's go ahead and solve for r and theta. This will just take a second here. We say r is always the square root of the squared components of this. So we say root 3 squared plus negative 1 squared. We get the square root of 3 plus 1 is the square root of 4. And we know that r is always positive. So we say r is equal to 2. So we have our magnitude. I shouldn't say magnitude. I suppose I should say the absolute value of this complex number. And then this direction angle right here. Well, if you recognize this is a 30, 60, 90, it kind of helps. But if you don't, we're saying again, we can find this direction angle here by saying it's the tan inverse of our y component or our imaginary component of this complex number over the x component, which is negative in this case. So if I said, okay, well, the square root of 3. I need this inner portion first. We say 3, take square root of that, divided by 1 that is negative, and you get this value right here. And if we do the tangent inverse of this, then we get an angle that is, look at that, negative 60. Now see, here's the thing. When you find this angle right here, we got to be careful. I'm just going to say 60, because that right there is a kind of a reference angle, loosely speaking. It is the angle formed between what you might call the terminal side of your angle and the x-axis. So we say that really what this is a 60 right here. So this doesn't tell us the direction angle. We're going to have to find it ourselves. But I do know that if the reference angle is 60, this is 180 minus 60, so this is 120 degrees. So all of this work, which by the way wasn't a lot of work, it was a Pythagorean theorem and a direction angle and sketching a picture. Once you have this, what we want to do is we want to say then writing this in trig form, which is, by the way, 2 cosine I sine 120 degrees, a number that is 2 units from the origin in a 120 degree direction. We are going to say that that is the same thing as this number here in standard form. And so what I want to do is I want to use DeMoivre's theorem now to find what would this be if I raised it to the 12th power. And so simply put, we could say, well, then it's 2 to the 12th. That's all that is. And we say CIS 12 times 120 degrees. Boom, we're done. As a matter of fact, we can get a value for 2 to the 12th. Shame on me for not knowing 2 to the 12th. 2056, 2050, 40, 4152. I'm going to get, I don't know. I'm going to guess here. 2 to the power of, let's see, where's my power button here? This, 12. Let's try that again. 2 to the power of 12. 4096. All right, so that's a good guess, huh? So we say 4096. And then we have cosine I sine, well, 12 times 12 is 140, so we get cosine I sine of 1440. And so this is totally accurate. As a matter of fact, this is this number to the 12th power. I'm going to do 2 things before we tune out of this video, but I'm going to reduce this angle as the first thing. I'm going to start subtracting 360 off of it for this 1440 until I get down to a number that's between 0 and 360. So we say 1440 minus 360 equals minus 360 equals minus 360 equals minus 360 equals. In this case, as a matter of fact, we get 0. So 4096. CIS 0, which means that this is a number that if we're thinking about this here, let's go back and see if I've made a mental calculation here error, because this number here is this one right here. So obviously it is not 4096. Okay, you know what? Actually, this is true. I was thinking about this number still. This is true, and this is because this is the 12th power of the number, not the actual number, which I kind of had a mental blip. So looking at this now, this 4096 CIS 0, what we can do is we could rewrite this in a standard form. So we say 4096. If I'm going back in a standard form, remember you would just distribute through this quantity right here. So I sine 0 degrees. And we should know that at 0 degrees right here on the unit circle, this is the 0.10, we get a cosine value of 1. So we get 4096 times 1, which is 4096 times 1, plus I times this 4096 here, if we're distributing, times the sine of 0, which is 1. So in other words, we get this right here. We get, sine of 0 is 0. We get this canceling out completely, and we just get 4096, which, by the way, if you were to graph 4096, 4096 would be this way at a 0 degree direction, 4,096 units away from the origin. And if I were to say what ordered pair would this be in standard form, it'd be 4096, 0, which just goes along with this kind of thing right here, which is what we just got right here. Okay, so that is how you raise complex numbers to a power. You just switch it into trig form and use DeMoivre's theorem. Cheers.